Okay, we're back for part 1C. Hopefully this won't take long, and then you guys can continue on studying. All right. So work energy and conservation of energy. First, work. Work is the force times the distance that the force is applied over. All right. So the force is applied from there all the way to there. Okay. If it's not applied over the whole distance, then it's not working. So this vector just kind of slides along. You're applying that force over that whole distance. You have the distance that you traveled as a vector. You have the force that's also a vector, and you have the angle between them. So we take the magnitude of the force, we take the distance that it moved, and here's the angle between them. And this is basically how we get our work out of this situation. Okay, so there's our work. Now, if you were to do the work of gravity, which is what we did on the test, the last test, we had the woman doing push-ups, and what we have is a force of gravity, which would be mg. We could write it as the force of gravity if you want. So we have this, and we want to know what the work is. So there's some mass. And what we do is we go, okay, well, what's the work of gravity? Well, instead of Fg, I'm going to write mg, and then I'm going to write the cosine of theta. However, if our distance that we travel is straight down, g is also straight down, so our force is straight down, and so the cosine of theta is 1 because theta is 0, right? So we would have our distance d. Sometimes when people are dealing with gravity, they use h, right? So our work would be mgh. Now, if we had to do the opposite of that work, then the work of the person opposing gravity would be minus mgh, right? We have to do that work. Gravity is doing this work. We are doing this work. If we're trying to slow this thing down. However, if we're pushing back up, then we are the one who is going from down here, and we're pushing back up here. We have to push with the same force, and therefore our work of the person is mgh. So that is again what we were doing in the problem of the lady with the push-ups. We were trying to come up with that. I do a bunch of stuff here. It's good to know which coordinate system and all that. I'm going to leave that to you guys to look over if you like it, if you don't, if you need to know it, if you don't. Some people do, some people don't. My desk is too high. Okay, let's do this. Friction work. Let's talk about friction work. And we've done this before. The work of friction or what have you. Let's just say we have a box, and the box is on a table, and we're going to apply a force to it, which means that we have some acceleration going in that direction. But we also have friction going this way. And our friction, we already talked about, is equal to mu times the normal force. We can put the normal force here. And we can put our gravity force there. And we want the work of the friction. Well, the box moves from here to here. So we're going to call that distance d. Okay. And the work of friction is going to be our force of friction, which is mu times mg, because the normal force is equal to mg. And we're going to go from, we have to multiply it by d, and then we also have to multiply by the cosine of the angle between this d, that's our d vector, and the actual force of friction vector. But they always oppose each other. It's 180 degrees. So no matter what happens, we've got minus mu mg d, because this right here equals -1. So the work of friction is always going to be negative. It's inescapable, okay? So get it right this time. No, what? Who? Why would you say that? Okay. Work energy theorem. Let's talk about that. It's not really super complicated. In case you didn't get it the first time, the work-energy theorem. Okay. So what is this thing that we're talking about? I'm going to just go straight for the actual, so all the net work that happened, all the forces combined did all their work, okay? So all of them are doing their thing. And what happens is that changes the kinetic energy of the situation. So if you have delta KE equals your net work, great, that is the answer. But what is delta KE? So let's get into it. Delta KE. And look, I proved it in class, but you don't have to see a proof of it. You just have to know. I'm going to give you what delta KE is. And first of all, it's the final KE minus the initial KE. Okay, but what I didn't write on the review is if you include both linear kinetic energies and rotational kinetic energies, then you have kinetic energy linear, finally, plus kinetic energy rotational, finally, and you're going to then subtract off your kinetic energy linear initially, and you're going to also subtract off your kinetic energy rotationally originally. So delta KE is that, and then you can go in and substitute those things. So 1/2 I omega final squared plus 1/2 mv squared. Oh, I switched them up. Okay, sorry about that. Linear, let's do linear first. This is v final, this is 1/2 mv initial squared, and then we're going to do 1/2 I omega initial initial squared. Okay, so that's your delta KE. But we just said that delta KE is equal to our work net. So you can do these things, add them and subtract them properly, and you will get your net work. The sum of the work. Not network. That's a movie from the 70s. Good movie, you should see it. Gravitational potential energy. There's really potential energy. There's really nothing more to say about potential energy, especially if you're dealing with gravity. I'm going to give you both here because I don't know if I talk about springs. Oh, I do. Okay, good. Gravity, if we're dealing with gravity, our potential energy is equal to the mass of the object times g times the height of the object above its most minimum point. Fine. What about springs? Oh, also, H can be negative. So if this is 0 and this is negative 42, which is the that H is less than 0, H equals negative 42. Okay, so your potential energy can be negative. So your potential energy is equal to negative whatever the mass is times gravity times 42. Okay, so you can have negative potential energy. With springs, with a spring, we don't have that same situation. So I have to draw, here's our x direction, here's our thing. This is where it wants to be normally. So that's 0. Here's our box. Here's the spring. And here's our center of mass. And at some point, we've got x here. And so if we say this is positive x in this direction, we've really moved in this direction. So our delta x for springs, our delta x is less than 0, which means it's negative. But the potential energy for a spring is equal to 1/2 whatever the spring constant is, so there's some spring constant associated, times delta x squared. So what if our delta x is equal to, well, let's make it negative 42. So if that happens to be negative 42, then our potential energy is equal to 1/2 k times negative 42 squared. But when you square a negative, it doesn't matter. It doesn't care. It's going to end up being positive. So no matter what happens, for a spring, potential energies for springs are always positive. So nice to know. It's a good little handy thing to know and to love and cherish. Okay, I'm getting tired. It's been a long day. Boom, 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 boom. I didn't talk about springs yet. So I'm going to just give you some of the equations. I gave you the potential energies for a spring. The force for a spring is minus kx. and I say minus kx because it's minus because the force of the spring is actually pushing or pulling to get it back to 0. Okay, it wants it to be at 0, and it's going to do everything it can to get it back there. Another thing is that we could be doing the work for a spring, it's got to be minus our kx times whatever the distance is that it traveled, right? So if you're multiplying kx times its distance traveled, it could be any distance, so I'm going to call it d. Okay, so why am I saying this? So we've got our box that would normally sit here, and it's here instead. And the work of the spring is pulling back to get it from here to there. Okay? So the distance that it's traveling is this distance. The force of the spring is going in this direction. So our work ends up being kx times d. Okay? The force is in that direction, the distance is in that direction, even though x is here. Now we don't do this very often. Why don't we do this very often? Because the force changes as kx, right? The force gets weaker and weaker and weaker. So now that I think about it, this is something that goes to the other class, and this little bit that I'm talking about right here, don't even worry about it. Don't even trip, dog. It's going to be fine. You don't even have to think about this. In fact, I'm going to stop. Ignore everything that just happened. It's a calculus thing. And you guys will get it later if you ever want to. Okay, so there's our force for a spring. Work done by gravity. We talked about that, so that's nice. Let's continue. Let's continue talking about springs. So let's move this up a little bit. And instead of doing an X out, which works pretty well, except it's ugly. Nobody likes that. Let's just erase a bunch of junk. There, let's get rid of that too. Okay, let's graph this thing. So here we have X. Here we have our force. I'm not gonna write it in a way. Okay. Let's write it in a way that this is our maximum force, max, and right here is 0. So that's our force max. We're going to come down through here, and we're going to end up with negative force max. So that'll be right here. And now all I have to do is draw a straight line through those things. Okay, nice. So minus k is our slope. Just like y equals mx, where m is our slope, right? All right. So the area, if you want to figure out the area, then we would say, okay, what is this area? And that area, this is x min. Do I want to call it x min? Let's just call it x. Let's get rid of the min part. Let's just call it x. On this side we have positive x. On this side we have negative x. It's fine. But our area is equal to 1/2 the base times the height. Okay? So we're going to take, I don't like using the x for times. We're just going to do 1/2 base times height. We know what the base is. The base is x or minus x. And our height is our f max. And we got to put our 1/2 here. We'll say our area is equal to that. And here we go. Lo and behold, I've got a minus x. And then the force max is minus kx. What? 1/2 kx squared. What? What does that look like? That is the work done, right? So we have two different things. And why? Because on this side, the work's positive. Down here, it's doing work also, pushing the exact other direction. However, this ends up being positive work too. So it doesn't matter which side you're on, it ends up giving you positive area work. Okay, so your work, no matter what happens, is the area under the fx curve, and it's 1/2 kx squared. Cool? This is negative force. That's where the negative sign goes away. That's how the negative sign goes away. Okay. So, great. Good job. Let's do the next thing. And the next thing is one of my favorite things. Okay, so conservation of energy. It's fabulous. What do we have? We could have some potential energy, and that potential energy could be anything. It could be mgh, it could be 1/2 kx squared, it could be gasoline, okay, whatever. So all those things could be our potential energy, and then we have some engine. Into our engine, we put the potential energy, and then out comes what? What comes out? That's right, kinetic energy. So we're taking potential energy and we're moving it toward kinetic energy, which is straight up 1/2 mv squared. 1/2 is just because we got to divide by 2, so that's not helpful. The mass isn't helpful because the mass isn't going to ever change, but the velocity gets squared. So whatever happens, we have taken and given ourselves a mass with a velocity because of whatever engine we're dealing with. Okay, we've got some engine, we had potential energy, and now we have 1/2 mv squared, which is our kinetic energy. So we get velocity out of it, right? Velocity out of our engine. Okay. So what can happen is we can have, like we did on the roller coaster, that's a great potential energy thing where we start off with this maximum potential energy and we end up, this is our minimum, this is somewhere in between, and here's our maximum. And it's just a great way to see how potential energy transfers to kinetic energy, but also back again, right? And especially if there's no friction, you can drop down and come back up, and you never lost any of the mechanical energy. So your total mechanical energy, let's slide up a little bit. Your total mechanical energy is this mechanical energy that you have in the system, what you can use mechanically. So that's your potential energy plus your kinetic energy. And it could be rolling kinetic energy too, all right? So it's both linear and rolling, rotating. So that's your total mechanical energy, fine. But your total energy for the system is equal to your potential energy plus your kinetic energy plus the work of all the non-conservative forces. And what is that? That's really basically saying friction, or forces that take energy out of the mechanical energy system. Then you can say, oh, well, I really want to put it in terms of my total mechanical energy. I can solve for my total mechanical energy and say that it's the total energy minus the work of the non-conservative forces at any time. So if you can keep these three equations straight, you're going to be doing just fine. And all you have to do is this one, and this one. You're good. You can do algebra to do the rest. So have those on your sheet and have a little algebra to do the rest, and you're going to be just fine. Okay. The next thing we have is power. And power, I like writing it like this, even though it's just a big P. I don't want you guys to get confused between different things. There's pressures and other assorted things, and I don't know. Power is equal to your work divided by time, and the units for that are watts, which is equal to a joule, 1 joule per second. So this is SI because joules are SI and seconds are SI. So watt is the SI unit, and that's what you want. All right, so, okay, power is that. Now, work, power is equal to your work, which is equal to a force times a distance, and you're dividing that by time. So distance divided by time, we all know what that is. That's a velocity or speed. So if you know your force and your speed, you can multiply those two things together and get your power. Okay, so that's one other way to do it. There's a third way. Your power is equal to your work, but work is delta KE, right? Divided by time. So you can put in your delta KE, and delta KE is typically 1/2 m V final squared minus V initial squared. And then we have time. I don't know why I have the 1/2 crossed out. Why am I crossing out the 1/2? I don't know why, but no. Oh, it's not a crossed out 1/2. I'm writing my 1/2 like this. Okay, good. Man, thank God. That didn't make sense to me. All right, so what are we gonna do? Let's do our example here, so you guys can. I don't know why I have an example, but I do. So in the example, we've got a car. It's got an initial velocity of 0. It has an acceleration of 3 meters per second squared. And it does all of this for a time of 2 seconds. So this is our example. A car. Mass is big M. Okay? So our force is equal to big M times our acceleration. And we know that V final is equal to our acceleration times time, so we can figure out that. 3 times 2 is 6, so it's 6 meters per second. Nice. And we're going to figure out the power. Initially, V naught we know is 0, so we're going to get rid of that. And so our power is 1/2 the mass of the car. And I wrote a little mass, and what I really want is a big mass, times V final squared. And we're going to divide by T, which is 2 seconds. And all in all, that's our power. I don't even, why didn't I give you a mass for the car? Let's do it. Let's say that the mass is 2,400 kilograms. Ooh, maybe it's more like a truck. So let's put all the numbers in. So now we've got 2,400. We've got V final squared, which is 36. 6 times 6 is 36. I'm going to come down here and I'm going to put my 2 times 2 seconds. That's 4. And the whole thing's going to end up being watts, so I'm going to write watts. And so now I can easily, you'd think I would be able to do it easily. My power is now 4 divided by 36 is 9. So it's 9 times, 36 divided by 4, sorry. 9 times 2,400. So 2,400 and 9 times that. I've got 21,600 watts. Okay, now I talked earlier about how you really should write this in scientific notation. You'd write it 2.16 times 10 to the 4, because we're going to go over once, twice, 3 times, 4 times. So 10 to the 4 watts. That's our power. This is the proper answer. okay? This one's okay. I'll accept. That's fine. But this is the right way. Okay. What else we got? That is part one. So part two starts as soon as you click it. All right. Good job.